should start. And the next talk is on a refinement of Gabriel-Ulmer duality by Frey. So you can start, please.
Thank you. Yes, so my talk is also about bioequivalences of two, also includes bioequivalences of two categories, and specifically I will talk about a refinement of Gabriel-Ulmer duality. So the talk is divided in three parts. The first part I will recall basics of the functorial semantics of algebraic theories and essentially algebraic theories. In the second part I will talk about clans as categorical representations of generalized algebraic theories. And in the third part, if I have time left, I will talk about models in higher homotopy types. Well, let's start with the algebraic theories. So the simplest case of algebraic theories are single-sorted algebraic theories. It's just a pair of a signature and a set of equations. And given such a single-sorted algebraic theory, we can construct a syntactic category where the objects are natural numbers and the morphisms from n to m are m tuples of terms in n variables modulo the equivalence relation generated by the equations. The syntactic category has finite products, and moreover, the set models of the theory correspond to finite product preserving functors from the syntactic category into set. So this observation motivates the definition of finite product theory. A finite product theory is just a small finite product category C. And a model of a finite product theory is a finite product preserving functor, again into set, or into another finite product category, but I will focus on set. So we denote the category of models by mod C, viewed as a full subcategory of the functor category. So for every object of the theory, the co-representable functor is a model, and that means that the dual Yoneda embedding of the opposite of the theory into the Z values functors co-restricts or factors through the models, and I will call this co-restriction Z. So we can do exactly the same and replace finite products by finite limits. Then we get the notion of finite limit theory. Finite limit theory is a small finite limit category. A model is the finite limit preserving functor into set. And it turns out that finite limit theories are more expressive than finite product theories. And structures definable by as models of finite limit theories include posets, categories, and so on. Again, for the co-representable functors are models, simply because home functors preserve limits in the second argument for every object in the theory, and we get this embedding of the opposite of the theory into the model. And moreover, in this situation, we can characterize the essential image of this embedding functor. And for this, we introduce some terminology. We call an object C of a co-complete locally small category X compact. And the traditional name is finitely presentable. I think compact has been used by Lurie, and I will use it because it's shorter. So we call an object compact if the co-representable functor preserves filtered co-limits. And a category is called locally finitely representable if it is locally small and co-complete, and the full subcategory on compact objects is essentially small and dense. And now then we can show that the models of any finite limit theory form a locally finitely presentable category. And moreover, the essential image of this embedding functor comprises precisely the compact objects. Sorry. We can show even more, namely that there's a bioequivalence of two categories between the two category of small finite limit categories and finite limit preserving functors, and the two category, the opposite of the two category of locally finitely presentable categories and functors preserving small limits and filtered co-limits. And so in one direction, giving a theory, we take the models as described already, and going back, as also mentioned, we take the opposite of the compact objects in the category. This bioequivalence is described in this book lokal präsentierbare Kategorien by Gabriel and Ulmer, and that's why it's called Gabriel-Ulmer duality. Okay, so it turns out that we can do something analogous, slightly more subtle, also for finite product theories. And that is described in the excellent textbook by Adamek, Rositsky, and Vitale called Algebraic Theories that I cite here at the bottom of the slide. And it works as follows. So in the finite product case, on the left, we have the category. So that's the top line in this rectangular diagram here. On the left, we have the two category of Cauchy complete finite product categories. In general, we cannot expect to reconstruct, we can only expect to reconstruct finite product theories from their models up to Cauchy completeness. And on the right, we have the opposite of the two category of algebraic categories. And an algebraic category is a locally finitely presentable category, which is bar exact and where the compact regular projective objects are dense. And then the corresponding functors are those that preserve the small limits, filtered colimits, regular epimorphisms. So then on the right, we just have the inclusion functor that exhibits the upper two by equivalence somehow is smaller than the lower one. But on the left, the forgetful functor goes in the other way, so we have to take the left by adjoint, which sends finite product categories to their finite limit completion. So there's also a formulation of this in terms of sifted colimits, but I won't use that for my purposes. I want the formulation with the exactness and regular projectives. Okay, so it's time to talk about clans. So as a motivation, the finite limit theories are great. They have a nice duality theory, but they are far from syntax. There are various syntactic counterparts or theories that are equally expressive as finite limit theories. There are Frey's essentially algebraic theories, Cartmel's generalized algebraic theories, which could also be called dependent algebraic theories because they use type dependency. And then we recently learned about Palmgren and Becker's quasi-equational theories, and I assume there are others. So the clans that I'm about to talk about can be viewed as a categorical representation of generalized or dependent algebraic theories. They're equally as expressive as finite limit theory, but finer. So they're closer to the syntax. And they retain more information from the syntactic representation of the theory. So the definition is a clan is a small category T with a terminal object equipped with a class T dagger of morphisms. We call it display map and write with a triangle arrow such that pullbacks of display maps along arbitrary maps exist and are again display maps, like in the pullback on the right. And display maps are closed under composition, and moreover, all isomorphisms and terminal projections are display maps. This definition is due to Taylor, who called such categories, I think, display map categories in his thesis. And the name clan was suggested by Joyal in this preprint Notes on Clans and Tribes, which is about models of type theory, dependent type theory. And indeed, we should think about clans in terms of some kind of type dependency. Specifically, you should think about display maps as dependent families. So think about it as the fibers of a display map as a dependent family depending on the codomain. And one observation is that clans in particular always have finite products because they have pullbacks over one, and the terminal projections are display maps. Examples for every finite product category, we can view it as a clan by taking all product projections as display maps. And finite limit categories can be viewed as clans by taking all maps as display maps. And we call that finite product clans and finite limit clans. So then the most important example is that the syntactic category of every Cartmel-style generalized algebraic theory is a clan. And so one very intuitive example is the clan for categories. So we know that the algebraic theory of categories can either be defined with one sort of objects and one sort of morphisms, or we can say we have one sort of objects, and for every pair of objects, a set of morphisms. And then this is the dependent type description. And we can kind of give a syntactic presentation where we would declare a type of morphisms depending on the objects, like here, and construct a syntactic category of that. And it turns out that this syntactic category, again, will be recovered as its opposite being embedded into the model, into the models. And it turns out this will be precisely the categories that are free on finite graphs. And the display maps in this case will be the functors that are induced by graph inclusions. Okay, models. So model of a clan is a functor to set that preserves the terminal object and pullbacks to display maps. Category of models is locally finitely presentable because a clan is a kind of finite limit sketch, and hence the opposite of the theory again. For finite product clans, the category of models is equivalent to the category of models of the finite product theory. And for finite limit theories, for finite limit clans, we also recover the desired models of the finite limit theories. And the models of this clan for categories is indeed the category of small categories. So one core observation is that the same category of models can be represented by different clans. For example, if I take an algebraic theory, then I can represent it by a finite product clan, but I can also represent it by a finite limit clan. And these are not equivalent. So that means if we want some kind of duality theory, we cannot hope to recover the clan from the category of models alone. And we have to equip the category of models with additional structure. And we do this in the form of a weak factorization system. Specifically, given a clan, we define a weak factorization system EF on the models. And we define it to be cofibrantly generated by the image of the class of display maps under this inclusion. And so the right class we call full maps, and the left class we call extensions. Specifically, I call an object a zero extension if the initial inclusion map is an extension. The same weak factorization system was also introduced by Simon Henry in a video seminar in 2020, and I have the link on the bottom here. Let's talk about full maps. So a full map is a morphism of models that has the right lifting property with respect to morphisms of this kind. And because we are in a functor category and set-valued functors, and the things on the left are co-representable, and we can transpose or unwind this, and we see that this condition is equivalent to the squares on the right. So these are naturality squares for display maps being weak pullbacks. And in particular, we know that terminal projections are display maps. Therefore, this kind of squares are weak pullbacks. And this just means that the components of morphisms of models, of full maps of models, are surjective. And from this, it's easy to see that they have to be regular epimorphisms. If, furthermore, the diagonals in the clan are display maps, then we can deduce that the squares of the right form are also weak pullbacks. And that would imply that the components of the natural transformation are also injective. And then this would mean that they're isos. And that means that for finite limit clans, the only full maps are for the finite limit clans, because they are all maps are display maps. Only the isomorphisms are full maps. So in the finite limit case, we get a trivial weak factorization system where the right class contains only isomorphisms. For finite product clans, on the other hand, the full maps are precisely the regular epimorphisms, and therefore the zero extensions, which are the things that have a left lifting property against the full maps, turn out to be precisely the projective objects. And that shows us that we are on the right track, because we want to, because the projective objects were used in this characterization of algebraic categories to recover the theory, or the opposite of the theory, from the models. So now we can try to reconstruct the clan from a category of models. Specifically, given a clan, we take C to be the full subcategory on compact zero extensions. And then indeed, this embedding Z from T op 2 models factors through this category. The category has an induced co-clan structure, and E, while not being an equivalence, exhibits C as a Cauchy completion of T op. And the proof of this is surprisingly subtle, and I will not discuss the details for time reasons, but I will mention that it uses the fat small object argument that is explained in this paper. So now we want to formulate a bioequivalence. And to this end, we give a definition of a clan algebraic category, and we do the easiest thing. We just say a clan algebraic category is a locally finitely presentable category with a weak factorization system that arises as category of models of a clan. And with this definition, we indeed do a contravariant, get a contravariant bioequivalence between a two-category clan CC of Cauchy complete clans, the functors preserving one display maps and pullbacks of display maps, and on the other hand, the two-category of clan algebraic categories and the locally finitely presentable functors that moreover preserve full maps. So, the definition of clan algebraic category is not very abstract or extensional. So it would be nice to have a more abstract definition or characterization. And indeed, so here is what we can do. We can show that a locally finitely presentable category with a weak factorization system is clan algebraic if and only if the subcategory of compact zero extensions is dense. The weak factorization system is cofinitely generated by maps between compact zero extensions. And moreover, we have a condition that says that for every compact zero extension and every object in the model of this of the compact zero extensions viewed as a clan, we have a certain colimit preservation property. And this condition, again, is not very explicit, and it's more or less just what we get if we write out what we want to prove and then unwind the condition that a certain functor has to be an equivalence. And so it would be nice to have an exactness condition similar to the one of Adam Krasicki and Vitale in the characterization of algebraic categories. And well, at least I have a necessary exactness condition. And let's recall that in algebraic categories, they have to be bar exact, and that means that all equivalence relations have effective quotients. And that can't be true in clan algebraic categories because all locally finitely presentable categories are trivially clan algebraic, and they're not all exact. However, we can show that for every clan, the category of models has full and effective quotients of component-wise full equivalence relations. And now the conjecture is that the condition 3 of this theorem is equivalent, or is implied by A having full and effective quotients of component-wise full equivalence relations. I don't know if I should call it a conjecture. I don't lean either way at the moment, but this is something that I want to settle. And that leaves me a few minutes to talk about models in higher types. So in the next 3 slides, I will write S for the infinity category of spaces or homotopy types. So this is the higher categorical analog of the category of sets. Okay, let's think about finite product theory or an algebraic theory, for example, the theory of monoids. Then we can define the corresponding finite product theory, C-mon, and the finite limit theory, L-mon. And of course, the respective categories of models defined as finite product preserving functors and finite limit preserving functors into sets respectively are equivalent because both are just the category of monoids. However, we can also consider finite product preserving functors and finite limit preserving functors from the respective categories to the to homotopy types. And then it turns out that in the case of the finite limit preserving functors, we again recover ordinary monoids with underlying sets. And this is just because finite limit preserving functors preserve truncation levels. And this is a one category on the left. So we end up in zero types on the right, which are equivalent to sets. However, on the other hand, if we use finite product categories, then we get a much richer class of models in higher types, which are known to homotopy theorists by A-infinity algebras, the kind of homotopy coherent monoids. The moral is, by being slimmer, the finite product theories leave room for higher coherences in higher types. This phenomenon has been discussed in this preprint by Sesnavicius and Scholz. I don't know if I pronounced the name right. And they call the models of a Levier theory in higher types, they call animated models. So they would call these things here animated monoids. So with clans, we can do even better because for the same for the same theory, we can give several different clanic representations that give rise to a hierarchy of different to models of different levels of strictness in higher types. And in particular, I have 4 different clan representations for categories, which I have listed here, where first 2 cases, the underlying category is the one that I described earlier, 3 categories on finite graphs. In the other 2 cases, we have all finitely presentable categories, and then 4 different classes of display maps. And if we model those in higher types, then we get structures that are well known in higher categories. Namely, we get Siegel spaces, Siegel categories, pre-categories, and discrete 1 categories, respectively. And with this, I stop. Thank you for your attention.
Are there any questions or comments?
Thank you for your talk. So 1 year ago, Ishiro and I did something similar, but instead of doing a weak factorization system, we study orthogonal factorization system, and then we replace, like, we have a different notion of clan that we call nest, and we also have
nest.
Yes, we call it nest. But so the paper, I will present it tomorrow. So
excellent.
So the title of the paper is Enriched Locally Generated Categories. And yeah, it's similar. It's not precisely the same, but because we work with orthogonal factorization system. But I think there we have I mean, you could try and look there for an inspiration for the characterization of algebraic categories you were looking for, because we have it in our case, and we so maybe something similar could work in your context.
Excellent. Yes. Could you send me the link to the paper?
Yes, I can. I will send it to
you. Thank you very much.
Are there more questions or comments? What about online? Are there questions?
Hello, back. Jonas, thank you for I'm glad to see my display maps are getting a little happening.
Louder.
I would point out that they were introduced for the situation where the category is not set, but fails to have all finite limits. And in particular, the diagonals are not display maps, or not in general display maps.
Yes.
I wasn't sure whether you'd taken that into account. But anyway, what I wanted to say is that I tried in my book to prove that categories of display maps are equivalent to generalized algebraic theories, but I'm afraid I got stuck.
Uh-huh.
And there's an admission as a footnote in chapter 8 of my book there. So it would be nice if somebody else could have another go at proving that, because after all, display maps are such a simple idea from the categorical point of view. It would be good if they could be shown to be equivalent to.
So I assume, were you able to show that generalized algebraic theories give rise to display map categories?
Yes, yes.
And the other direction
One direction is easy. Going the other direction, starting from semantics and going to syntax, is always very difficult.
I see.
And it would be nice to see somebody else having another go at that problem.
Okay, that is very helpful. Thank you.
Okay. So no more questions. So it's time to thank the speaker.